3, 2, 1, now. Taken off.
We start our journey on the scorching concrete of APJ Abdul Kalam Island off the coast of Odisha, breathing in the salty sea air mixed with the harsh, pungent aroma of burnt, solid rocket fuel. You look at the raw, utilitarian beauty of the vertical launch system standing proud against the coastal sky. Twin grey canisters sit angled towards the heavens, held aloft by a robust heavy duty steel frame laced with thick hydraulic lines and massive safety chains. This launcher represents the brutal mechanical reality of modern air defense. It looks rugged, designed specifically to withstand the blistering heat of a rocket exhaust plume and the corrosive marine environment alike. Before any fire breathes from those canisters, the administrators carve out a massive chunk of the sky. The Notice to Airmen, or NOTAM, paints a sprawling blue polygon across the Bay of Bengal. This hazard zone claims a radius of 102 kilometers, effectively sanitizing a massive arena for this high speed gladiator match. They clear out every commercial airliner, every fishing boat, and every wandering seagull to ensure a pristine testing environment. This specific NOTAM reveals the true reach of the M1 interceptor, defining a localized battle space where the missile stretches its legs and hunts down the electronic ghost mimicking a hostile aircraft. Now direct your attention to the sterile, brightly lit environment of the Spacetech Industries facility. Here, the Kusha M1 interceptor rests horizontally on a precision calibration bench. Engineers scrutinize every millimeter of its olive green and black fuselage. This view gives us a pure, unobstructed look at the aerodynamic philosophy. The design screams efficiency. You see the forward canards, the long cylindrical body housing the solid rocket propellant, and the rear tail fins designed for aggressive maneuvering. Contrast that sterile lab environment with the raw violence of the launch itself. The missile shrieks off the launch pad, riding a blinding pillar of incandescent white flame. The M1 interceptor looks incredibly sleek, slicing through the dense, humid coastal air. Notice the distinct booster section at the very bottom, right where the flame erupts. This booster provides the initial violent kick, overcoming the inertia of the heavy missile and blasting it past the speed of sound in mere seconds. Once the booster spends its fuel, it falls away, leaving the main sleeker body to ignite its own sustainer motor and continue the hunt. This sleeker profile and extended range trace their lineage directly to the massive leaps Indian scientists made in solid propellant chemistry. The Astra air-to-air missile program served as the ultimate crucible for this technology. DRDO chemists spent years perfecting the specific impulse of their solid rocket fuel. They utilize hydroxyl terminated polybutadiene as the primary rubbery binder. They mix this polymer with coarse crystals of ammonium pertorate acting as the oxidizer. They sprinkle in microscopic flakes of pure aluminum powder to dramatically increase the combustion temperature. This precise chemical cocktail burns at incredibly consistent rates. They pour this slurry into the motor casing around a star-shaped central core. This specific geometric shape ensures the burning surface area remains constant, providing a perfectly smooth thrust profile. Better energetics mean you squeeze exponentially more thrust out of a smaller physical volume of fuel. This propellant research pays massive dividends across the entire missile ecosystem. A smaller, lighter missile experiences reduced aerodynamic drag, allowing it to fly further and maneuver harder. DRDO hitting the simulated target on their very first attempt proves the maturity of this underlying technology. Local missile production stands as the single most vital pillar for waging a sustained air defense campaign during a prolonged war. Modern conflicts devour munitions at a terrifying pace. Look at the situation unfolding globally. The United States currently bleeds its inventory of Patriot Pac-3 missiles at a pace far exceeding their manufacturing speed. They fire $4 million interceptors to swat down cheap, mass-produced drones and rudimentary rockets. The American military-industrial complex sweats profusely trying to replenish these depleted stocks, forcing the Pentagon to desperately purchase older, larger, and historically less effective Pac-2 missiles just to keep the launchers armed. This reveals a glaring systemic vulnerability. You have to appreciate the irony of firing a luxury sports car equivalent into the sky to destroy a target constructed from plywood and stolen moped engine parts. The S-400 system provides India with a formidable shield, but relying on Russia for a sustained supply of interceptors during a crisis requires immense optimism. The Russian industrial base remains entirely consumed by their own grinding war effort. Their factories run triple shifts, merely trying to replace the missiles they expend daily in Eastern Europe. Expecting them to fulfill export orders while their own cities face aerial bombardment requires a monumental leap of faith. Importing these systems drains the national treasury at an alarming rate. The success of the Kusha missile test shifts the tectonic plates of regional security. By mastering this technology natively, India seizes total control over the production lines. When the storm clouds of war gather, the factories in Hyderabad and elsewhere instantly ramp up manufacturing, churning out fresh interceptors around the clock. This indigenous approach slashes the cost per unit drastically, allowing the military to build overflowing warehouses of ammunition. Wars of attrition are won by the side that keeps firing on day 100, and domestic production guarantees that staying power. The ongoing conflicts in the Persian Gulf and Eastern Europe demonstrate vividly that robust, endlessly resupplied air defense forms the bedrock of national survival. Let us plunge into the granular, microscopic physics of how this interception actually unfolds in the real world. The entire kill chain begins with the eyes in the sky. The Netra Mark 1 airborne early warning and control aircraft cruises at 30,000 feet, scanning the horizon. This platform utilizes an upgraded gallium nitride based active electronically scanned array radar. Gallium nitride represents a magical leap over older silicon based chips. These specialized semiconductors handle immense thermal loads, allowing the radar to pump significantly more electrical power into the transmit modules. Older silicon based chips suffer from severe thermal limitations. Pushing too much voltage through a silicon chip turns it into a tiny puddle of melted slag. Gallium nitride features a much wider band gap, allowing electrons to flow freely and efficiently. The engineers crank up the voltage safely, pushing massive amounts of electrical power into the radar array. The heat dissipates easily through advanced liquid cooling channels. This generates a microscopic electromagnetic wave that travels at 300 million meters per second. The Netra radar fires concentrated pulses of this electromagnetic energy out into the atmosphere. These invisible waves wash over the hostile aircraft or incoming cruise missile. A microscopic fraction of that energy bounces off the metallic skin of the target and reflects back towards the Netra. The receiving modules catch these faint echoes. The onboard signal processors perform incredibly complex fast Fourier transforms, filtering out the background noise of the earth, the clouds, and the weather. The computer calculates the exact three-dimensional coordinates of the target, including its latitude, longitude, altitude, and its precise velocity vector. The Netra immediately packages this tracking data into a secure encrypted radio frequency transmission and beams it down to the Kusha battery waiting on the ground. Because DRDO owns the source code for both the Netra radar and the Kusha command center, this data handshake happens seamlessly, instantly, and flawlessly. Two systems built by the same engineers speak the exact same digital language. They share a unified data protocol. Buying systems from different countries forces you to rely on clunky software translators that introduce latency and errors. Owning the source code eliminates this friction, creating a unified, sprawling ecosystem of sensors and shooters acting as a single living organism. Upon receiving the target coordinates, the Kusha system springs into action. The battery switches on its own massive ground-based AESA long-range radar to illuminate the target, or it operates in stealth mode, firing the interceptor based solely on the continuous data feed pouring in from the Netra AWACS. The launch sequence initiates. An electrical current ignites the solid rocket booster. The M1 interceptor violently erupts from the canister, accelerating straight up into the sky. As the missile punches through the lower atmosphere, it constantly receives mid-course updates from both the ground radar and the AWACS simultaneously via a specialized data link. The target moves fast, so the intercept point constantly shifts. The missile must fly towards where the target will be, predicting the future geometry of the engagement. The flight computer onboard the interceptor digests these data link updates and calculates the necessary course corrections. This brings us to the breathtaking mechanical ballet of the flight control system. The missile steers itself using those aerodynamic fins we saw in the laboratory footage. At speeds approaching Mach 5, the physical environment becomes incredibly hostile. We must calculate the exact aerodynamic forces at play here to understand the sheer brilliance of this engineering. A missile flying at Mach 5 travels at precisely 1715 meters per second. At an altitude of 10 kilometers, the surrounding atmosphere possesses a density of roughly 0.41 kilograms per cubic meter. The dynamic pressure slamming into the fuselage reaches an astonishing 596,000 pascals. To change direction, the onboard computer sends a digital pulse width modulated signal to the servo motors located near the base of the fins. These servo motors are marvels of electromechanical engineering. Electric current flows into copper coils, generating a magnetic field that spins a central rotor. This rotor connects to a titanium planetary gear system, multiplying the torque while reducing the rotational speed. This immense torque pushes against the control surface, tilting the fin against the roaring slipstream of air. Imagine the sheer precision required in this chaotic environment. The motor engages its planetary gears, tilting the aerodynamic fin by exactly one single degree. This tiny rotational movement exposes the fin surface to that massive wall of air, instantly generating roughly 1490 newtons of lateral lift. We assume the spent interceptor weighs roughly 300 kilograms at this stage of flight. Dividing that force by the mass gives us a lateral acceleration of nearly 5 meters per second squared. Over a brief 5-second window, that single degree of tilt pushes the interceptor a staggering 62.5 meters away from its original path. If the motor tilts the fin by 2 degrees, the deviation exceeds 125 meters. The target aircraft occupies a very small volume of airspace. The servo motors must flutter hundreds of times every second, making micro adjustments to keep the weapon perfectly centered on the predicted intercept trajectory. The engineering tolerances mirror the precision of a Swiss watch operating inside a roaring blast furnace. The flight computer rapidly processes the incoming sensor data, adjusting the pulse width modulation to ensure the fins move with microscopic accuracy. As the Kusha M1 interceptor closes the distance and enters the terminal phase of the engagement, the environment changes again. The missile is now just a few dozen kilometers away from the hostile aircraft. Relying purely on the data link from the ABAX loses its effectiveness for the final millimeter perfect strike. At this precise moment, the missile awakens its own onboard active AESA seeker located in the nose cone. This miniaturized radar functions exactly like the massive arrays on the ground, shrunk down to fit inside a cylinder a few inches across. The seeker blasts the target with its own high frequency radio waves, obtaining an incredibly high resolution track. The target aircraft suddenly realizes a missile is painting it directly. The enemy pilot frantically dumps chaff, deploys electronic countermeasures, and pulls violent, bone crushing evasive maneuvers to break the radar lock. The Kusha flight computer ignores the chaff entirely. It filters out the electronic jamming using advanced algorithms marketed by the DRDO scientists. The servo motors work in overdrive, tilting the fins with violent aggression to match every single evasive turn the target makes. The interceptor bleeds off some of its tremendous speed as it pulls high G maneuvers, but the advanced solid propellant sustains enough energy to run down the prey. In the final microseconds before physical impact, a specialized radio proximity fuse triggers the warhead. A direct kinetic strike demands absolute perfection, so the missile detonates a few meters away from the enemy aircraft to guarantee destruction. A spherical wave of high explosive shatters the casing of the warhead, sending thousands of tungsten fragments tearing through the air at hypersonic speeds. These fragments shred the wings, the engines, and the cockpit of the target, instantly transforming the multi-million-dollar fighter jet into a falling cloud of debris. This entire sequence, from the initial detection by the Netra ABAX to the final devastating detonation, happens in a matter of minutes. The seamless integration of the gallium nitride radars, the dual pulse rocket motors, the precision servo actuators, and the encrypted data links proves the extraordinary capability of the Indian defense sector. The successful test of the Kusha M1 interceptor validates decades of painstaking research into aerodynamics, material science, and software engineering. It sends a resounding message across the geopolitical landscape, confirming that the nation possesses the industrial might and the scientific brilliance to protect its skies with a truly indigenous, world class shield. This achievement fundamentally alters the strategic calculus of any adversary contemplating an aerial intrusion, forcing them to face a relentless, domestically produced wall of fire. Building the missile acts as the initial step in a much larger strategic framework. Maintaining a high state of operational readiness across dozens of squadrons requires a colossal logistical and training effort. The military constructs specialized storage bunkers, climate controlled maintenance facilities, and secure transportation networks to handle these highly sensitive munitions safely. The technicians responsible for servicing the gallium nitride radars and the solid rocket motors require years of rigorous specialized education, transforming them into elite guardians of the technology. Furthermore, the integration of the Kusha system into the broader integrated air command and control system mandates a massive upgrade to the communication infrastructure. The armed forces lay thousands of kilometers of secure high bandwidth fiber optic cables and launch dedicated military communication satellites to ensure the data link between the Netra airbarks, the ground radars, and the launchers remains unbroken. The system functions smoothly in the face of intense electronic warfare. Every single piece of this sprawling puzzle fits perfectly together to guarantee the safety of the airspace. Let us delve deeper into the immense challenges associated with managing the thermal dynamics of a missile traveling at Mach 5. As the Kusha M1 interceptor tears through the atmosphere, the friction between the air molecules and the outer skin of the missile generates astronomical temperatures. The nose cone and the leading edges of the control fins experience the most severe heat buildup, often glowing cherry red during the flight. The engineers at DRDO utilize exotic materials to prevent the missile from melting itself into slag. They wrap the internal electronics, the sensitive radar seeker, and the explosive warhead in layers of advanced thermal insulation, ensuring the delicate circuitry remains cool and functional while the exterior surface faces a literal inferno. The structural integrity of the missile body demands equal attention. Carbon fiber composites and aerospace grade titanium alloys form the skeleton and the skin of the interceptor. These materials offer an exceptional strength to weight ratio, keeping the overall mass low while providing the rigidity needed to survive maneuvers exceeding 30 or 40 times the force of gravity. When the servo motors slam the fins hard over to intercept a jinking fighter jet, the entire missile airframe undergoes immense bending stresses. The Kusha M1 absorbs the punishment, translating that violent stress into a blistering change of direction. We return to the fascinating world of the active electronically scanned array radar, the true heart of both the Netra airbarks and the Kusha ground battery. Traditional older radars relied on a massive heavy dish physically spinning in circles to scan the sky. This mechanical rotation consumes precious time, creating a dangerous blind spot for fast moving targets to slip through undetected. An AESA radar eliminates moving parts entirely. The flat panel features hundreds or even thousands of individual solid-state transmit and receive modules. Each tiny module functions as its own independent mini radar. The computer controls the timing of the radio pulses emitted by each module with staggering precision, adjusting the phase of the waves by fractions of a nanosecond. By slightly delaying the pulse from the modules on the left side of the panel compared to the modules on the right side, the combined radar beam electronically steers itself across the sky at the speed of light. The radar looks left, right, up, and down instantly, tracking hundreds of individual targets simultaneously. This immense radar power proves crucial for detecting modern, low observable targets. Stealth aircraft utilize specialized shapes and radar absorbent coatings to scatter and absorb electromagnetic energy, returning a tiny fraction of the radar wave to the receiver. Weak, older generation radars lack the power to see these faint echoes. The massive energy output of the gallium nitride AESA radar burns through this stealth protection, illuminating the target and painting a clear picture for the Kusha battery to act upon. The software managing this entire network stands as the most complex component of the entire project. Modern air combat happens at a speed that vastly exceeds the processing capabilities of the human brain. By the time a human radar operator manually spots a target, calculates its trajectory, and pushes a button to launch a missile, The enemy aircraft has already flown dozens of kilometers and dropped its payload. The Kusha system relies on advanced artificial intelligence and machine learning algorithms to automate the entire kill chain. The battle management computer constantly ingests gigabytes of data from the Netra AWACS, the ground radars, and the satellites in orbit. It analyzes the flight profiles of every single object in the sky, instantly distinguishing between friendly commercial airliners, flocks of birds, and hostile incoming missiles. When it identifies a threat, the AI calculates the optimal intercept trajectory, assigns a specific launcher to the target, and prepares the missile for flight, all within a matter of microseconds. The human commanders supervise the system, holding the authority to abort a launch, but the machine handles the raw mathematical heavy lifting required to fight a hypersonic war. The strategic implications of fielding such a capable system reverberate far beyond the borders of India. For decades, the global air defense market existed as a duopoly dominated by the United States and Russia. Nations seeking to protect their airspace were forced to choose between these two suppliers, navigating complex geopolitical strings attached to every single purchase. The arrival of the Kusha system disrupted this established order, offering a potent, domestically produced alternative that rivals the performance of the most expensive foreign systems. As India continues to refine the technology, integrating newer variants of the interceptor with even longer ranges, the protective bubble stretching across the subcontinent grows larger and more impenetrable. The M1 interceptor, with its estimated range of 150 kilometers, provides the crucial inner layer of defense, shielding vital military bases, industrial centers, and population hubs from tactical threats. Future iterations like the M2 and M3 variants will push that boundary out to 250 and 400 kilometers respectively, creating a deeply layered overlapping net of destruction. This multi-layered approach forces any potential adversary into an impossible dilemma. To strike a target inside India, an enemy aircraft must first survive the long-range gauntlet of the S-400 and the upcoming Kusha M3 interceptors. If the pilot manages to evade those massive missiles, they then enter the medium-range kill zone of the Kusha M1 and the Barak 8 systems. Finally, any munitions that slip through face the short-range fury of the Akash and the point defense cannons. The sheer volume and diversity of these overlapping defensive systems make a successful aerial campaign prohibitively difficult, deterring aggression proactively. The successful flight test represents far more than a technological triumph, it signifies a massive leap towards true strategic autonomy. The engineers at DRDO and the private sector partners at Spacetech Industries have proven their ability to design, build, and deploy world-class weaponry using domestic talent and resources. This achievement secures the skies, strengthens the industrial base, and ensures that the nation dictates the terms of its own defense, free from the constraints of foreign supply chains and external pressure.